Hello guys, today we will be building this buck converter module based on the LM2596 chip in KiCad from scratch. We go in detail step by step on how to place parts, create the schematic, lay out the PCB, and how to write traces. So let's get started. To find the exact chip we will be working with, go to your favorite electronics distributor and search its name. There are many types of this buck converter IC, but you need to look for the one with this abbreviation, which means it is the adjustable version. Once we find the right chip, we can open the datasheet. Here we can see that are listed all the major features of this buck converter. For example, the existing versions, which packages are available, how much current it can output, the maximum input voltage, the ability to turn off the IC with transistor-transistor logic, TTL for short, its current and temperature safety features, and its high efficiency, to name a few. To build our module, we need to find the so-called typical application circuit. At the end of this page, we can see the circuit for the fixed output voltage versions, which is not what we need, as we're using the adjustable type. To find such circuit, we need to scroll down a bit in the datasheet. Here it is. As you can see, we just need a handful of components to make this IC work. We need an input capacitor, a catch diode, an inductor, an output capacitor, a couple of resistors to set the voltage, and finally an extra capacitor. Now that we know what we need to build our module, let's jump into KiCad to create our project. Go to File and click New Project. Select the default KiCad project template, give it a name, and save it in a folder. Double-click on this icon to open the schematic editor of our project. Let's start by placing the IC. Press A on your keyboard, or go to this icon and search the name of the chip. Here we see all these different options, like we did before, but we are interested in the adjustable version. You can see that there are two options of the same chip. That's because there are two different packages available. The TO220, which is a through-hole package, and the TO263, which is an SMD package. I'll choose the SMD version. Let's also add the external components required. Click on the same icon as before and type C_polarized. This is because both the input and output capacitor are electrolytic capacitors, and thus polarized. Open the Choose Symbol window again and type L for a generic inductor. Press R to rotate and place it near the capacitors. Do the same thing to find the diode and the first resistor. The second resistor needs to be variable, as its resistance changes the output voltage. And finally, we will need an extra capacitor. This time it needs to be unpolarized. Now I place the components we just added, just like the datasheet, to make the schematic clear. Here we go. Now we need to draw these very simple connections following the datasheet. And here is our circuit wired. However, these components still have generic values. To know which values to assign to each component, we can read the datasheet, that will tell us everything. The only thing that I'll change is this diode package. Instead of using the THT package, I'll choose an SMD smaller equivalent. And here is our schematic updated. You might ask how I calculated the resistance of this potentiometer. If you go back to the datasheet, we read that the output voltage follows this formula. I wanted to have a buck converter that can output almost the entire range of voltages that it is capable of, so 37 volts. Using this formula, we can easily find out that in order to output 37 volts, we need an R2 value of 29 kiloohms. Unfortunately, there is no potentiometer with this value, so I'll go with a 25 kiloohm one. The module will output around 32 volts, which is more than enough in my opinion. You might have noticed that I didn't give a value to this capacitor. If we check the datasheet, it will tell us that this component is required for an output voltage greater than 10 volts, and there is a table with all the values based on the voltage you want to output. The problem is that if you're using this module to output more than one voltage, you really can't pick the perfect value, and if you're using it to output a voltage smaller than 10 volts, you won't need it. So unless you're planning to use the buck converter for just one specific output voltage, you can simply remove this capacitor and the module will work just fine. Now the module is technically complete, but I wanted to add an LED to visually know if the buck converter is working. To do so, click the symbol icon and type LED. We also need to add a current limiting resistor to prevent the LED from being destroyed. Let me add these two components to the schematic. And here they are. We need to place the LED after the output capacitor so it will see a much cleaner voltage. I chose a resistor value of 4.7 kilo ohms because it protects the LED enough throughout the output voltage range of this buck converter. We're almost done with our schematic. We just need to add a way to actually connect some wires to the board. To do so, we can add mounting holes with pads and connect them to both sides of the buck converter. Before assigning the footprints to our components, if you wish to output more than one voltage value with this board, you need to change this variable resistor with a potentiometer. Otherwise, keep it like before and use the formula we saw earlier to calculate the resistance of R2. I'll change it into a 25 kilo ohm potentiometer. Now click this icon and let's assign the footprints. For the input and output capacitors, I'll choose this package. The diode I chose has an SMA package, so I'll choose that. For the LED, I'll choose the 0603 package, as it is quite small. The 4 mounting holes will be 2.2 mm wide, and we want the pad to be both on the top and the bottom. For the inductor, I'll choose this package. For the 2 resistors, I'll go with the 0603 package again. And finally, for the potentiometer, we need to select the potentiometer THT library and choose the 3296W footprint. And we're done. Now we need to convert our schematic into a PCB by clicking this icon. Then click here to update the PCB from schematic, click Update PCB, and then close. You will see all the footprints we selected appear on screen. To make the PCB layout easier and more clear, disable the fabrication layer so that it is not as crowded. Now, I'll make a rough layout of the PCB, trying to have a feel for where components should go. I came up with this. It doesn't have to be perfect immediately. You can always make adjustments later. Now, let's clean up the layout a bit. I remove the mounting holes designator, as we replace it with text later. Then, it is good practice to have all the designators facing the same direction. Now, we need to draw the board outline. We do this by selecting the Edge Cut layer and using the Rectangle tool. Draw a rectangle around the components. Once we've done that, we can start connecting components together. We use copper pores instead of traces for important connections to improve performance. Select the top layer and click on this icon to draw a field zone. Click where you want your copper pore to start. Select the pad connection to solid and select the net name. In this case, is DC in. Click OK and start drawing the region. Once you're done, click B on your keyboard to build the copper pore. We do the same thing with the ground. Select the tool, select the net name, set the pad connection to ground, and start drawing. Now we need to do the same thing for all these other nets here. Here we go. For the remaining connections, we can use traces. Select the line tool and with a track thickness of 0.5 mm, start connecting everything together. Here you can see that these two rat's nests are crossing. We can rotate the resistor so that we can route our connections more easily. Here I realized that when I placed the potentiometer, I left this pin unconnected. To fix this, we can go back to our schematic and connect the wiper to the feedback node like this. Then go back to the PCB editor and click the Update PCB from schematic icon. Click Update PCB and hit close. And now we can connect this pin to the feedback node. Our PCB is looking great, but we are missing the last ground connections. To improve stability and performance, we can build a copper pore on the bottom layer of the PCB, just like we did before. Select the net, and once you finish drawing, hit B on your keyboard to build the copper pore. To access this plane, we can use so-called vias. Select the top layer and click on the Place Vias tool. Place it right next to the pad you want to connect, and with the line tool, route a trace from the pad to the via. I'll do the same thing with this pad. I also moved this designator here to make some space for later. I realized that we have some unused space here, so we can shrink the PCB to make it tighter. Here we go. You can see that there is still a bit of space between components here that could be optimized, but for a board like this, I think it's more than enough. Plus, if you will be hand soldering the components, a bit of extra room can be useful. As a final touch, we can write the pad connections on the PCB so we instantly know how to connect our module. Select the seal screen layer and select the text tool from the menu. Increase the height, the width, and the thickness a little and type your text. Click OK, R to rotate, and place it wherever you want. Then do the same thing for the remaining 3 pads. And our PCB is finished. To view its 3D model, go to View and then 3D Viewer. To download the files you need to have your PCB manufactured, go to File and then Fabrication Outputs. Here you can download the Gerbers as well as every other file type. That's it for this video. If you found it useful, leave it a like and consider subscribing to the channel. For more tutorials and videos, click on one of the suggested videos on screen. Thanks for watching and I'll catch you in the next one.